So, section 8.4 is on Taylor polynomials. So we're going to go back and cover this section before we finish chapter 10 because it's kind of the easier version of what we'll do in the last section of chapter 10. So the idea of this section and also of section 10.7 is asking about how we might approximate a non-polynomial function with a polynomial. And hopefully you did something like this in Calculus 1. There was an idea called linear approximation. And in that, the idea was we took a function and we did linearization to that function, sometimes called L of x, and that was a way to approximate f of x by using the sort of equation of the tangent line. So we did f of a plus f prime of a, and then times x minus a for as a way to approximate a function near the value of a. And so you might have done that in Calculus 1. And the idea is we're going to take that and expand upon it. So obviously, if we have a function that looks something like this, and we use linear approximations, and we draw the tangent line, which that one doesn't look very good, but in theory this is a tangent line at this point. That's a straight line, and it does a pretty good job of approximating pretty near a. But maybe if we could draw a quadratic at that point, right, that would probably be even a better approximation. Or if we could think about drawing a cubic function, maybe that would be even a better approximation. So instead of just using linear functions, maybe instead we use a polynomial function. And that's where these ideas of Taylor polynomials come from, is to use a polynomial instead of just a linear function, a higher degreed polynomial, to approximate a function that maybe is not a polynomial. So here's the formula, the nth Taylor polynomial for f. We're going to say it's centered at c for any n that you want to use. So you get to decide how many degrees you would like in your polynomial. So this is Tn of x for an nth degree polynomial. You're going to start out with your f of c plus f prime of c, and we're going to divide by 1 factorial times x minus c, plus the second derivative evaluated at c over 2 factorial x minus c squared. And then you continue that pattern all the way down to the nth derivative evaluated at c over n factorial and times x minus c to the n. So this is the equation for a Taylor polynomial. And there's a special class of Taylor polynomials that are centered at 0. So if you imagine plugging in zeros for all those c's, that makes a lot of this polynomial a lot nicer because you don't have the x minus anymore, because the c would make that go away. So those have a very special name, and those are called Maclaurin polynomials. So we'll talk first about those because they're a little bit easier to work with since we don't have to be centered at a particular number. So we're going to look at 2 examples. We're going to start with f of x equals e to the x, and we're going to talk about the nth Maclaurin polynomial for this function. So the way to create the nth polynomial is to, we need to find, if you go back up here and look at this equation, we need to know what f of c is, we need to know what f prime of c is, we need to know what f double prime is, all the way up to the nth derivative. So the idea is we have to get a pattern for that derivative so that we can use the pattern of the derivatives evaluated at c to determine what the pattern will be for the polynomial. So these are really kind of pattern recognition problems. That's what a lot of the Taylor polynomials and later Taylor series questions will look like. So we'll start with f of x and note that f of 0, we're doing Maclaurin polynomials, so we're plugging in 0, is e to the 0, which is 1. And then if we do the next one, f prime of x, hopefully you recognize, is also e to the x. And if we plug in 0 to that, we get 1. So the first derivative evaluated at 0 is 1, the function evaluated at 0 is 1. And hopefully this pattern is easy to recognize since the derivative of e to the x is always e to the x. And so it looks like we're always going to get 1 for all of our derivatives. So if we're writing down Tn of x, it's going to be 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus, and we'll do our dot 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 all the way up to 1 over n factorial x to the n. So that would be the Taylor or the Maclaurin polynomial for e to the x. Because our derivatives on top, so these are the only thing we really have to solve for. Everything else is given. So all of the derivatives on top evaluated at 0 are 1. So we just have those values that we've plugged in all the way across, and that gives us the Maclaurin polynomial for e to the x. We can do a similar process to do the Maclaurin series for sine of x. It's a little bit more complicated. So we'll start over here. G of 0 is sine of 0, which hopefully you recognize. Sine of 0 is 0. Now we'll go to the derivative. Hopefully you recognize the derivative of sine is cosine, and we're going to evaluate that at 0. So g prime of 0 is cosine of 0, which is 1. If we take the second derivative at 0, we're going to get a negative sine at 0, which is going to be 0. And if we take the third derivative, I think you'll see that we get negative cosine of 0, which is negative 1. And then the next derivative, I believe, goes back to sine. So you get this kind of repeating pattern that goes sine, cosine, negative cosine, and then back to sine. So every fourth derivative, we're back to sine, and then we repeat that pattern. So hopefully that's easy to recognize in the process of taking the derivative of sine, that it does return back to itself eventually. So as we try to write the Taylor polynomial for this, we will, maybe I'll add a page here so we can take care of this. Let's see. So we had g of 0 was 0, g prime of 0 was 1, g double prime of 0 was 0, and then g triple prime of 0 was negative 1, and then we said this pattern repeats. So as we're trying to write out the Taylor polynomial for sine of x, we'll have 0 plus 1 over 1 factorial x to the n plus 0 over 2 factorial, sorry, not x to the n, just x squared plus negative 1 over 3 factorial x to the third plus dot dot dot, and we'll maybe keep going here. And just keep in mind, we have to kind of figure out the pattern, and hopefully we can kind of notice that the evens are kind of going away, right? So the even ones have a 0 derivative. So we're going to be getting rid of all of the even exponents for this Taylor polynomial, Maclaurin series polynomial, since it's centered at 0. So if you think about the very last term of this, it's not x to the n because we don't have every n. We only have the odd n's. So our last exponent is x to the 2n plus 1. And then we're going to divide by 2n plus 1 factorial. And then on top, notice that we're alternating pluses and minuses. And when we plug in the first n that we would start at is n equals 0. And so we would have, looks like it's evens and odds. And so I think it's negative 1 to the n that we'll want to use as the pattern that we're noticing. So if we're trying to think about this, actually I guess this no longer becomes x to the t sub n, it's actually t sub 2n plus 1, because of the fact that we actually are using this for the odds, and that will be equal to t sub 2n plus 2, since the evens are zeros, so every even one will be the same as the odd one before it, because you would just be adding a 0 on for that next term. So this one is a little tricky just because of the fact that we eliminate the evens, so we actually don't get tn, we get something that looks more like of a tn plus 1. And the reason that happens is that we see that the derivatives of the even powers go to 0. So all of the even powered terms are going to go away in our Taylor polynomial. And we're only left with terms that have odd powers. And so as we think about what the pattern would be as we go far enough out, the last term is not just going to be a random n term. We have to be careful here because we could have just odd terms, or actually we do have only odd terms. So when we look at the last term, the exponent should be 2n plus 1. That's how we can write odd numbers. divided by 2n plus 1 factorial because the exponents are matching the factorials, and then thinking about alternating -1, +1, and since the very first term when we start at 0 is positive, looks like the negatives will be on the odd ends, and so we want to have -1 to the n. So this is t sub 2n plus 1 of x, and that's what we have here. So if we want to write that a little bit nicer, t of 2n plus 1 for x is going to be x minus x cubed over 3 factorial. You could say plus x to the 5th over 5 factorial, because remember we're taking only the odds. We can go plus dot 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 all the way down to -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So this is the Taylor series. It is also the same, not Taylor series, sorry, Taylor polynomial, and in particular the Maclaurin polynomial for sine of x. Tn plus 1 or Tn plus 2 is equal to this particular process. So this one is a little bit different than the first one that we did because the first one the derivatives were all the same. But here just remember that the even terms are being canceled. We're left with the only odd terms, and we have to figure a nice way to write that. I have one more example that we'll do. This one is ln of x, and so we need to start taking derivatives to see if we can figure out what the pattern to the derivatives will be. So h of x is ln of x. So h of 0, let's actually make this x plus 1 so that we don't end up with an undefined first term. So this is ln of x plus 1. H of 0 excuse me, is ln of 1, which is 0. The first derivative of ln is 1 over x plus 1. So 1 over 0 plus 1, which is 1. The second derivative, evaluated at 0, is going to be -1 over 0 plus 1, which is going to be -1. The third derivative of h, I guess, is going to be 2 over x plus 1, in this case 0 plus 1, so we get a 2. And then the fourth derivative at 0 will be 2 times -3, excuse me. 2 times -3 over 0 plus 1. This is now raised to the 4th. Squared, I guess, over here. So we're getting a whole bunch of different values for this derivative, and the idea is that we want to figure out what that's going to be as we write it as a polynomial. So if we start to write this out, looks like we'll have 0 plus x over 1 factorial minus x over 2 factorial plus, it's x squared, excuse me, plus x cubed over 3 factorial. We're going to put a 2 on top, and then plus -2 times a -3 over 4 factorial x to the 4th, and then we're going to keep going. And the question is, what is the last term? Like, what's the pattern that we see here? That's kind of the idea. So if we're looking at this, let's move this one out of the way for right now. We'll continue to work on this example. If we're looking at this one, we want to think about what the pattern is. So we get definitely x over 1, and then x squared over 2. Here, the 2 and the 3, or the 3 and the 2, the factorial, 3 factorial, and the 2 on top will cancel, and you're just left with x cubed over 3. And then the next one will be a minus, and if we think about the 4 factorial and the 2 and the 3, the 2's and the 3's will cancel, so you're just left with a 4 in the denominator. So hopefully the pattern is clear now. So we're canceling, it looks like. So in fact, we can even get rid of this factorial because 2 factorial is the same as 2. So it looks like we're left with x to the n over n. The factorial ends up canceling with the exponents on top. And then we have to take care of the -1. And it looks like the negatives are occurring on the even exponent, so we need to do n plus 1. So this is the Taylor polynomial, in particular the Maclaurin polynomial for ln of x plus 1. We'll look at this last example in class so we can see one example together.